went for a postdoc at the School of Natural Science in Princeton. She was also a NASA Public Fellow and an IPC Fellow. She won several prizes, among them she has been named the Scientist of the Year in 2018 by the Harvard Foundation. And actually, she's professor at Harvard University, and her research interests are dark matter, neutrino, and other early physics, and physics of the early universe.
Thank you. Yeah, okay, thank you. Thank you very much for the introduction, the invitation. Yeah, it's really nice to be here. So I will be using the board. So bear with me with my handwriting. It will not be the best, but it will be a learning experience for you and for me. So these are I decided to write down the whole outline of the 4 lectures that I will be giving. So basically, this is the beginning of 4 lectures in statistical methods in cosmology. I'll be not giving a rigorous introduction to the topic, but the goal instead will be to give you enough information so to fuel your interest, to start to give you a general picture of cosmological data analysis, and hopefully that will be fuel for you to go on and learn more. Okay, so the outline for these 4 lectures, we'll see how it goes, is the following. We'll start with the hypothesis of ergodicity. We will move on to Gaussian random fields, start talking about correlation functions and power spectra, and I will talk a little bit, hopefully today also, about moments and cumulants, a little bit about survey geometry and pseudospectrum. Let me see. Yeah. No. Yeah. Then we will move on to talking about Bayesian and frequentist interpretation of probability in the context of cosmology. I'll be talking about likelihood and telling you in general how likelihood analysis works, modeling of data and statistical inference, talking about goodness of fit and maximum likelihood and contours, confidence level intervals. We will talk about Markov chain Monte Carlo likelihood analysis. I will try, to explain it. If we have time, we will go in more detail. If not, it will, it will just be an introduction to the topic. We will talk about Fisher analysis because it's like a standard kind of back of the envelope thing that cosmologists like to do when predicting the results for future surveys in particular. To various degrees of complexity. And if I have time at the end, I would like to talk about a new technique that has been developed by French mathematicians about 10 years ago and that I have been pushing forward with my group, which is called wavelet scattering transform. And here, so I believe this PDF will be saved in case you don't want to write down everything. Here I put down the bibliography. Some of the, I use several things to write these lectures, but some of the bibliography, like the foundations of this whole method, statistical methods in cosmology, can be found in this already old book by Robert Lupton, Statistics in Theory and Practice. This is how I started learning about this. This is an old book also by Stewart and Orn, Advanced Theory of Statistics, and some papers, you can find these papers, and there are lots of, papers that refer these papers, but some of these papers are a paper by Trota and by Licia-Verde. Okay? Okay, so let's get started. Let's see how I do with this board. Yeah, awesome. So we'll get started with hypothesis of ergodicity. I would like to talk a little bit about this. which is something that we use a lot in cosmology. So basically, when comparing the results of theoretical calculations to the observed universe, we don't focus on the density contrast of matter, for example, at a particular point in space. Instead, we predict the average properties of statistical properties of the density contrast. And in addition, we consider that the universe we live in is a random realization of all possible universes that could have been a realization of the true underlying model, okay? So all the possible realizations of the true underlying model, that of course we don't know, but we try to learn, makes up an ensemble, okay? And a crucial assumption of standard cosmology analysis is that the part of the universe that can be observed, we observe a patch of our universe, is a fair sample of the whole universe. That's an assumption that we make. We only have one universe to observe. We think that that universe is a realization of an ensemble, so we make the assumption that the universe that we observe is a fair sample of all possible universes, of the whole universe, sorry. And this is closely related to the cosmological principle, okay? So this is, the statistics of the universe have, the statistics of the universe has to be considered as an average over the ensemble. But in cosmology, we have just one universe, okay? So the fair sample hypothesis states that we have just, that samples from well-separated parts of the universe are independent realizations of the same physical process, okay? So then the hypothesis of ergodicity follows. And basically, this says that averaging over many realizations is equivalent to averaging over a large enough volume. Okay, so this is the hypothesis of ergodicity that says that averaging over many realizations, sorry about my handwriting, is equivalent to averaging over a large volume. You see, the problem is that we only have one realization. So we use parts of the volume as a fair sample of the universe. There. Great. So the cosmological field that we are interested in is just a realization of a statistical process. Okay, we measure our universe, and we think that that's a realization of an ensemble of all possible universes under the underlying true model. Of course, we don't know the underlying true model. This is what we are trying to learn. Okay, and we will see how we learn about it along these different lectures. Okay, so to start to talk about, data analysis in cosmology and probabilities, etc., I thought I would start from the beginning and start talking about Gaussian random fields, okay, in the context of cosmology. So let me, see, we're moving very quickly from 1 to 2. Let me write Gaussian random fields like this, okay? So Gaussian random fields are commonly used in cosmology, and they have several advantages. Basically, there are strong motivations from inflation to assume, you probably saw with Merdad, to assume that the primordial fluctuations that gave rise to the present-day universe, the present-day structure that we observe today, follow a Gaussian distribution. And the main advantage is that it is possible to compute the statistical properties analytically. The analytical properties of Gaussian distributions are very easy to compute. Basically, for a Gaussian distribution, the mean and the covariance completely specify the distribution. Okay, so Gaussian distribution is completely specified by the mean and the covariance. Okay, so let's focus on the density fluctuations that you probably started discussing with Marco yesterday. So their distribution cannot be, we know that the distribution of density fluctuations of matter cannot be exactly Gaussian. That we know, okay, because it's bounded below. So in general, the density contrast, we write the density contrast delta as, well, delta is, you know, the density of matter, say, in the universe, okay, minus the mean over the mean, okay? We know that this guy has to be greater or equal than -1. Yeah, so it's bounded by below. Yeah, it's bounded by below. And so this implies that it cannot be, you know, we know from here that if the density contrast is very large, it cannot be a Gaussian. We have a cut at -1. However, if the density contrast is small enough, a Gaussian distribution can be a good approximation, okay? And we know that the density contrast at the very beginning in inflation started being small, okay? We know from observations that it started being, and from our, you know, model of the universe, that it started being small. So, you know, we can approximate it, at least in the very early universe, by a Gaussian random field. Okay, so if the density contrast is a Gaussian random field, so if delta is a Gaussian random field, with average 0, let's say, it's the PDF, the probability distribution function of this density contrast, can be written as follows. I will just write the Gaussian, okay? So let me write the vector delta. Let me write it like this. Sorry, I will write it like this. This will be the probability of delta, and this will be 1 over 2 pi to the n over 2, where delta, anyway, let me write this. You know, this is not important for this. So let me just write what I want to write, which is, this is 1 over the square root of the determinant of the correlation matrix times e to the minus 1/2 delta transpose c to the minus 1 delta. Okay? Well, delta again is the density contrast. C is the correlation matrix whose elements are defined by the following. So Cij, probably you saw this with Marco, the correlation matrix, or no? Okay. The correlation matrix, or perhaps you know this from before, but it can be written as delta I, delta J. You may have seen it written in this way, okay? Where this is a function of separation between 2 points. By the way, when I put delta sub I or delta sub J, means the density contrast evaluated at position Ri, or the density contrast evaluated at position Rj, yeah? Okay, so, right, good. So an important property of Gaussian random fields, this is under this approximation. Of course, afterwards, this approximation breaks down, and there are several things that you can do. It's not appropriate anymore. At some point, this approximation will break down, and it will be not appropriate anymore to consider a Gaussian random field, okay? But bear with me. We're just starting. Let's consider everything simple. This is a Gaussian random field. This is a good approximation for now. And an important property and a useful property of Gaussian random fields is that the Fourier transform of a Gaussian random field is still Gaussian. So what does it mean to have a Gaussian random field? That the PDF for the density contrast at any point in space is Gaussian, okay? This is valid at any point in space. Okay, so, yes? R, here? Yeah, this is the position. So when I write delta I mean delta evaluated at position Ri, yes? Is the position where I'm evaluating. Could you tell me your names? I would like to remember the names afterwards. So when you ask a question, please tell me your name also. Greco? Yes, name? Augusto.
What is the meaning of the dots and Greek letter?
This? Just the correlation function. We will actually move on now to write down the correlation function. This is what I mean by the correlation function. See the ensemble average of two density contrasts evaluated at different positions in space. Yes, your name? Yeah, actually, the vector could be, what's your name? Gustavo. The vector, I mean, in any position, right? I can write delta 1, sorry, not 1. No, 1 second. Delta 1, delta 2, blah, 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 until delta n, okay? Yeah? Yeah. Okay. Let's look at, as Augusto was asking, let's look at correlation functions and power spectra and moments and cumulants, okay? Let's see, hopefully we will be able to write this down. Okay, so I just wanted to make a very brief introduction to Gaussian random fields so we are all in the same page, okay? Let's move on. So, yeah. Let's look at correlation functions and power spectra. So I will now write some basic expressions for correlation functions and power spectra, okay? So let me start by writing a universe that is a cube, like writing these expressions in a universe that is a cube of volume V, then we will take this to infinity, okay? And I will start with a universe that is a cube with volume V with periodic boundary conditions, okay? So, well, in general, if you have some function, okay, you can write, let's write this, if you have a function f of r, yeah? We can write the Fourier transform of this function. I will put a tilde every time I write a Fourier transform, okay? I'll write the Fourier transform of this function as, funny, I touched this, okay. I'll try to avoid being too obsessive with deleting everything. I'll write the Fourier transform as follows, as a Fourier transform. E to the, this will be our convention, e to the ikr, yeah? Okay, so if this is the Fourier transform, the inverse Fourier transform will have a factor of 1 over volume, okay? 1 over volume times the sum over k of f of k e to the minus I k r. Okay? Okay. Now let's consider that our function is the density contrast. Okay? Okay, so the density, when we will be taking f as delta, and again, the correlation function that I wrote before with this symbol over here, of r minus r prime will be written as an average, okay, of delta of r and delta of r prime, okay, where the averaging is over all the possible configurations of the random field, yeah? Now, if the field is Gaussian, all of the information will be contained in the power spectrum. Of course, when the field is non-Gaussian, there is more information that is contained in other moments or cumulants. Okay, there was a question? Or yeah, what's your name? Nicolas. Yeah, it could, okay, sure. Yeah, we can consider, I'm just considering a volume that is discretized in different wave numbers k, but you know, you could, in principle, 1 over the volume of the sum this goes to an integral of d3k 1 over 2 pi cube. Yeah?
I said that you can do it with, you have a lot of lambda points. You can transform to zoom to integrate.
Yes, exactly. Yeah? I'm just taking the discrete version. Right. So when we have a single, okay, so remember this ergodicity hypothesis, okay? In fact, we have a single realization, but we are trying to take it as a fair sample from an ensemble of different realizations, okay? Now, for a single realization, in general, what we can do is define an estimator of this correlation function, okay? As the special average over pairs separated by whatever distance you choose to consider, yeah? Now you can write, you measure one universe, okay? So you can write an estimator for the correlation function. And this estimator for this correlation function, I will write, in general, I will write estimators with the hat, okay? This is, in general, how it's done in the literature as well. Okay, so this estimator of the correlation function at a particular distance, now r is the distance that I'm considering, okay, can be written as 1 over the volume, an integral over d3 r prime, delta r prime, delta r plus r prime, okay? Here we are using translational invariance, okay, which is kind of another way of using the ergodicity hypothesis. So, but here I'm using translational invariance because I'm saying that this correlation function only depends on the distance between the 2 points. Okay, sorry, I should write r minus r prime here. Okay, to make it more clear. Yeah? Okay, now, what is this is, yeah. No, you're right. Sorry, I'm integrating. I'm integrating over r prime so that let me, yeah. This is r. Thank you. Yeah? Okay. Now this is the estimator of the correlation function in the universe that we measure. The true correlation function is the expectation value of this. Yeah? So what's the expectation value of this guy? Let me write it. The expectation value of the estimator of the correlation function is what? Is 1 over v, the integral of d3 r prime, the expectation value of delta R prime delta of R plus R prime. Yeah?
Okay, we cannot say the true correlation function because if without the cut, because we have only universe. In the bracket, we are average of the set of universe.
Well, so remember that the average implies that we are averaging over many realizations of different possible distributions, but we consider that in practice, many different parts of our universe can be a fair sample of many different universes, okay? Okay, but what I want to show you here is that the expectation value ends up being the correlation function, yeah? This guy, remember that this guy, as I defined it, is the correlation function, yeah? Not the estimator, just the correlation function. And so then you have a trivial integral over the volume, over the volume, okay? That cancels out. So in the end, what you have is that the average over the the average over the estimator of the correlation function is the correlation function. Yeah? Okay. You can do the same with the power spectrum. You can define an estimator of the power spectrum. You see the difference in what I'm doing? I'm defining an estimator because I have one universe, I'm measuring a correlation function. That's my way of estimating the true correlation function. And what I'm showing you is that if I take the ensemble average, or, as I showed you before, you can also take average of the correlation function over many different parts of the universe, that is equal to the true correlation function. So we are in business. That's a good estimator. Yeah? You can do the same for the power spectrum. You can define an estimator for the power spectrum. I will end up using a lot of this because my handwriting is very big. But you can define an estimator for the power spectrum, yeah? As 1 over V delta, the Fourier transform of K, and the Fourier transform conjugated of K prime. Yeah, this is, anyway. You can, sorry, yes? Gabriel, thank you. Yes.
The average of the estimator equal of the average of the correlation function itself?
The average of the estimator ended up being the correlation function itself. Correct. The average of the, so I'm taking the average of the correlation function is already an average, okay? It's already an average over, remember how it's defined, the correlation function is already an average, it's already an average over the density contrast, yeah? The correlation function is an average over the density contrast. The estimator was not defined as an average, so I'm saying that the average of the estimator is the correlation function itself. Eric? Yes, correct. That, thank you, Eric. Very good. This means that this is an unbiased estimator. Awesome. Thank you. Yeah. Okay. So we can do the same with the power spectrum. And here I wrote it wrong because it doesn't depend only on K, but it also depends on K prime. Okay? Okay. It could, in principle, be any function of K and K prime. So I will write it this way. Okay? So, you know, you can show taking the expectation value. So if you take the expectation value I'll show you something that may seem trivial, but it's actually not. So if you take the expectation value of this power spectrum, okay, of this estimator of the power spectrum, yeah, what does this mean? Well, I'm taking 1 over v, I'm rewriting this, delta, the Fourier transform of delta, and delta conjugated, yeah, I'm just rewriting what I wrote above, okay? If I take this expectation value and I rewrite the Fourier transform of delta in terms of the density contrast in real space, okay? I do the whole calculation, it's super simple, it's 3 lines, but I wanted to save time here, okay? If I do this, I can show that this is equal to the following, to the integral, these 3 are the correlation function, okay? E to the I k r delta kk prime, where this is a delta Kronecker, okay? This guy, we call it the power spectrum. Not the estimator of the power spectrum, but the power spectrum. So what am I showing here? I'm showing that the average, the ensemble average of the estimator that I build for the power spectrum is equal to the power spectrum. That's an unbiased estimator. And I'm also showing that the power spectrum is the Fourier transform of the correlation function. It's not that obvious to start with. It's obvious that the Fourier transform of the density contrast, you know, you can write the Fourier transform of the density contrast in real space and in Fourier space. But here I'm showing that also you can write the Fourier transform of the correlation function and it ends up being the power spectrum. Okay? And this result, so, yes?
My name is
Juan? Why is this a Kronecker delta and not a Dirac delta? You end up having, what's the calculation? You end up having, well, it could be, it depends if you're in the discrete limit or the continuous limit, yeah. Yes, what's your name? Gabriel, yes. No, I forgot, yes.
No problem. Why are you defining the split of the whole spectrum this way?
Well, I thought it was, you know, it's a kind of a sensible way because the estimator of the correlation function also had 2 deltas, and here we are in Fourier space, so a sensible way. I also am cheating because I know that in this way the power spectrum ends up being, the estimator of the power spectrum ends up being an unbiased estimator. Yeah. And there are ways of building unbiased estimators, you know. It's not magic, like, yeah, we can go over this. Yes. What's your name? Greco. Ah, see, I'm being. And at the same time, that's right. Yes, that's right. Right. It's defined on certain scale, right? I'm defining in terms of a distance in R, for example. So I can plot it as a function of scale. Is that the question? Correct. For several scales. The question is if you have to take, sorry, I have been forgetting to ask the question again. The question is if you can take the average. Well, this is a function of scale, so you have to take the average over different scales. Yes. All right. So I wanted to show here just that the power spectrum, it's not so obvious. The power spectrum can be defined as the Fourier transform of the correlation function. Okay? From now on, just because I will be lazy, if I write a vector, if I write R or K without the vector, it means the absolute. So this notation will mean the absolute value of the vector, okay? And so on. Okay, great. And also going back to Gabriel's question, I think it was your question about the delta, Kronecker, etc. No, it was Juan's question. The delta, Kronecker, or Dirac, but the delta itself is a result of translational invariance. Yeah, great. And again, as I said before, I just wanted to say here, I'm taking everything over the volume, over some size. The universe has some certain volume, okay? But when you go to infinity, this factor of 1 over the volume times the sum over k goes, yeah, as I wrote before, okay. Remember that I'm writing here everything in terms of the volume because, I don't know, I find it easier to write it that way, okay? But if you want to go to infinity, then 1 over the volume times the sum will go to 1 over 2 pi cubed times the integral, okay? Okay, so here, when we are working with a Gaussian random field, the phases of the Fourier modes are random, and the real and the imaginary part of the coefficients have Gaussian distributions. Okay, these deltas, when I tell you that they have Gaussian distributions, well, they can be complex, right? They can have a real part and an imaginary part, okay? So the amplitudes of those parts will have a Gaussian distribution, and the phases will be random, yeah? Great. And again, if the field is Gaussian, I'm sure all of you know this, but if the field is Gaussian, the power spectrum defines everything, okay? Contains all of the information. But our universe is not that simple, as obviously you know. There is gravity, so the galaxy, when you form galaxies, the large-scale structure of the universe is highly non-Gaussian, okay? So for example, at 1 megaparsec scales, you saw this with Marco perhaps, or you will see it, but clusters are over density contrasts of order 1,000, okay? And obviously, because delta has to be greater than -1, you know that there are no delta equal -1,000 regions, so this is highly non-Gaussian. You see, departing, I'm writing something obvious perhaps, but departing from delta being very small, okay? When you depart from there, you have a highly non-Gaussian, well, you have a non-Gaussian universe, and it becomes highly non-Gaussian when you depart more and more, okay? But it ends up happening that when you form galaxies or clusters, these density contrasts are very large. So you're talking about highly non-Gaussian fields. So to completely specify, what do you do to specify a non-Gaussian distribution? Well, it's hard to know when you completely specify, because something that is Gaussian is Gaussian. Something that is non-Gaussian could be non-Gaussian in many different ways. Yes? Because delta has to be greater or equal than -1. So if delta is 1,000, you know that you have a cut, right? So if I plot the probability distribution of delta as a function of delta, right? You know that it's a cut here. So you know that it has a cut, and if you're in regions over here, yeah, this is highly non-Gaussian. If you're around 0, the tails, you can go to -1, but that will be in the tails. Okay, so it's a full topic in cosmology, how to measure non-Gaussianity in the large-scale structure, in the CMB, in different fields, okay? And there are different ways in which you can measure non-Gaussianity. The classical way that people have been using for over 20 years, perhaps, is to look at the different cumulants, okay? So you can define moments or cumulants in the following way. I will write it down, but I just want to mention this just in general. People have been looking at the bispectrum or the trispectrum of the galaxy density field or the CMB and trying to measure non-Gaussianity from those cumulants, okay? There are other ways, and if I have time, I think I will. In the last lecture, I will go over some other technique in which you can learn non-Gaussianity. What's the information contained beyond the power spectrum? That's the whole topic, right? If the field is non-Gaussian, there is more information beyond the power spectrum. How do you learn that information? Okay, so I will go over the traditional way right now, but before I will take 2 questions. Brian. I wanted to take the Fourier transform in the easiest possible way. So I consider one volume that then I will extrapolate to infinity. Okay? Yes. Facundo. The what regions? Voids, yes. Yes, the underdensities. That's right. Yes, correct. They're not, yeah. Yeah, he's asking if the voids have a density contrast. Sorry, Facundo is asking if the voids have density contrast that are negative, so they also become non-Gaussian. Non-Gaussian doesn't mean that the power spectrum doesn't have any information. It means that the power spectrum doesn't have all of the information, yeah. Or voids as well, right, you can study there are lots of studies by lots of people. Anyway. But Ben Wandel, for example, is one example. Over the years, he has been studying the information content in voids in the universe. Yeah. Okay, last question. To estimate, sorry? Not with the power spectrum. The polyspectra, that's correct, yes. Not all yes. So the question is what are the methods that, I guess the question is, what are the methods that we are going to study here to understand non-Gaussianity? Is that? Yes. Yes, there are lots of ways, that's true. There are Minkowski functionals, there are wavelets, there are polyspectra, lots of different ways. I will touch base on some of these ways, not on all of them. But we can talk about them afterwards. Okay, but let me start with that, exactly following up on what you're asking. Let's start from the traditional way in which the field has been studying non-Gaussianity over the past, say, 20 years. So by the way, I assume that this is known. I said that, so again, I mentioned that gravity makes the structure that we think starts in a Gaussian way non-Gaussian, right? Because gravity attracts more, matter attracts more matter due to gravity. And so you start forming massive structures, so the distribution becomes highly non-Gaussian. This is already, so we know that the large-scale structure of the universe is non-Gaussian today. Nothing at all related to inflation, sorry, yeah? The universe may have started with a Gaussian, you know, in a Gaussian way, without non-Gaussianity, but you end up having non-Gaussian, a non-Gaussian distribution of the large-scale structure of the universe. So this is called, anyway, these non-Gaussianities are one type of non-Gaussianity we know is there, not exotic, we know it happens, we understand the physics. The other types of non-Gaussianity that people look for are primordial non-Gaussianity. What if the universe during inflation started with a field, with a distribution that is non-Gaussian? And people try to understand this primordial non-Gaussianity in order to understand the physics of inflation. That's another type. That's non-Gaussianity, but it's the same non-Gaussianity, right? But coming from another physical process. Okay. In any case, this class is on statistical methods, so let's see how do we study non-Gaussianity. So we can define central moments as follows. So we can define central moments as follow. I will call the moments mu and the cumulants k, okay? So moments can be defined as the expectation value of x minus the expectation value of x to the power m, okay? Where these averages, what are these averages? Averages are defined over a particular probability distribution, okay? So the average of a function f, say, is defined as the integral of dx, f of x, the probability distribution of x, okay? This is the probability yes, probability distribution. Okay, so, you know, you can define, you know, mu2 is the variance, okay? Mu2 is called the variance. Mu3 is called the skewness. These are terms that come up in the non-Gaussian literature. Mu4 is called the kurtosis, and so on. Okay? And this, all these, so again, so for Gaussian random fields, the cumulants are 0 for odd order point functions. Okay? And all the moments for Gaussian fields are specified by mu1 and mu2. Okay? The mean and the variance. Now, you may also see in the literature people not only talking about moments, but people talking about cumulants. Okay? So let me write down. So the moment, so here mu2 is equal to, the cumulant of order 2. I'll write it down. Mu3 is equal to the cumulant of order 3. Mu4 is related to the cumulant of order 4 in the following way, plus 3k2 squared, and so on. Okay? So what is a cumulant? Let me write only cumulant of order 2. Okay? This one is equal to x1, x2 minus x1, x2. Okay? You can see that this one it will be, well, let me write it down because x1, x2, x3 minus combinations, right? Minus x1, x2 x3 minus x1, x3, x2 minus x2, x3, x1. These kind of things are better not to say, but just to write. Okay, and I will not write the cumulant of order 4 because it's longer. Okay, so if the field is non-Gaussian, people go on and study, moments or cumulants, and in order to gain some information about the field. Not necessarily all of the information is contained in the first 3 cumulants. It depends what type of non-Gaussianity the field has. If the field is highly non-Gaussian, you may need other methods because it becomes more and more expensive, right? You need to be evaluating the field, different numbers of field, yeah? When you move on to different cumulants, you need to be evaluating different numbers of fields, and to calculate the error, you need many realizations, so you need to simulate this many times. You need to calculate this every time. So it becomes more and more expensive. That's what motivated me and my group to start studying the non-Gaussianity with a method known as wavelet scattering transform. It's not the only method. I'm just excited about this method. That's why I will talk about this method. So I may not be talking about other methods just because I want to focus. If I have time for one method, I will choose my favorite one at the moment. If I have more time, I will choose other methods. I will talk about other methods. Okay, good. How much time do I have? 20 minutes, excellent. So what I wanted to do in what follows is start talking about survey geometry and pseudo-power spectrum. But let me pause for a second and take questions, if there are more questions. No? Okay. What I wanted to do now is to start talking about survey geometries, okay? You can obviously, things are not perfectly Gaussian and they are not observed in an infinite universe, okay? So, surveys in general that go and measure the galaxy density field, for example, galaxies, have measured in a certain patch of the sky. And it's not a perfect circle or a perfect cube, okay? They just measure in different patch of in a patch of the sky, but with some weird shape, okay? And from there, you need to estimate the correlation function or the power spectrum. So you need to take into account the geometry of the survey. Why am I saying this? Okay, let me write down here. Well, survey geometry. Now we start talking about, how things happen. We start getting closer to how things happen in reality, and it starts getting messy, okay? Survey geometry, and I will talk about pseudo power spectrum, okay? So surveys have boundaries. So we need to add these, we need to incorporate these, fold this into our analysis through what is known as the window of the survey or the mask of the survey, okay? So imagine I have, a box as we saw before, okay? I have a box of volume V, we are all happy, we can make Fourier transforms, and then the Fourier transform of the correlation function is a power spectrum, all great. But now I tell you, no, I come and I measure with my telescope and I subtract the point sources and the galaxy and all sorts of things, and this is the true delta, the true density field lives in this infinite box, but my survey geometry has some weird shape, okay? And I measure here, inside this region, okay? So what I need is to fold into my analysis a survey window or mask, okay, where inside this window, inside this window, I will multiply by 1, and outside of the window, I don't observe, so I will multiply by 0. Yeah? That's the idea. Yes?
Can I think that?
Augusto, no.
Yes,
Yes, Augusto.
Can I think it like a CMB mask?
Yes, it could be in the CMB, it could be in the large-scale structure. By the way, I'm talking about delta here, referring to the large-scale structure, but this same thing happens with the CMB, okay? In fact, I think I will write down some example for the CMB. Every survey measuring any field in the universe will have a window or a mask. CMB, galaxies, whatever, you name it, okay? There will be a mask. Okay, so this is a real space multiplication effect. So let's talk about delta. I could talk about ALMs of the CMB as well, okay? So the observed delta at the point X will be what? Will be the true delta at the point X times a window function, okay? And I want my window function, and it's this, it has this complicated shape. I want my window function to take values of 1 inside and 0 outside, okay? Okay, so this is a multiplication in real space, which becomes a convolution in Fourier space. So in Fourier space, this will become delta observed of k will be delta true of k, and this is the symbol that I will use for convolution times the window function in k space, okay? So for wave numbers, or k modes, that are of the size of the survey, this effect becomes relevant, okay? And it's not like some exotic effect. It's real. I'm measuring a patch of the sky. And it happens to be the case that the sharper the window function is in real space, the more it rings in Fourier space, right? Because the Fourier transform of a sharp function has ringing on Fourier space. And this couples different k modes. So people try to avoid these sharp features of the window function with some process called apodization, okay, where the window function doesn't go abruptly from 1 to 0. Sometimes you multiply by an exponential or a Gaussian, okay? But that's, it depends on it depends on the analysis that you're doing. You will use different apodization techniques. But that's a detail. That's a detail. I just wanted to mention it.
What is the purpose of the apodization?
The goal of the apodization, the question is what is the goal of the apodization, is to avoid fictitious coupling between different k modes. Yeah, coming from convolving a ringing, multiplying by a sharp function or convolving with a function that has ringing. Question by Neha, yes.
So my question was, so in examples of these functions that we use, is there any physical motivation to have it be something that's like a Gaussian or an exponential that dies out at the edges? Like, are we measuring galaxies worse at the edges of the volume? Is that what we're trying to do? Or would it need to be more complicated?
So you mean for the apodization?
Yeah.
You need to choose the apodization so that the apodization technique, it depends on what wave numbers you want to measure, but you don't want to add, fictitious effects that are not there, okay? So there is no rule for apodization. People do different things. But in general, yes, you measure galaxies worse at the edges, and the k modes of the galaxy at the edge will be, depending on what you want to measure, you may be coupling different k modes that are not coupled in reality. So you want to avoid that. How you avoid it? There are different ways. There is no standard rule for that. Susana. So hopefully not. People work hard on trying to do, to do this apodization technique so that it doesn't affect any result. If it affects, it's a wrong apodization, definitely. You should check that, that you're not screwing up stuff, that you're not getting results that are not real, okay, with this technique. Yeah. Okay, yes, so what I wanted to say before we finish, what do I have, 10 minutes or? Yes, okay, perfect. So what I wanted to say is that the power spectrum with the window function, so when you take into account the window function, the power spectrum is called the pseudo-power spectrum, okay? And it is not the Fourier transform of the correlation function anymore. So let's take an example of the CMB. I just took this example because it's a little bit easier to write down. Example. So for the CMB, okay? So for the CMB in general, I know. So you can see what I'm used to do in the chalkboard. I'm used to erasing with my hands. That's why I end up covered white. So for the CMB, I can write the ALMs. Yeah, you probably saw this with Julian last week. Yeah, you can write the ALMs as the integral over the solid angle of the variation in temperature at some position of the sky times YLM conjugating of n. No, this is the perfect case in which you're measuring in a sphere, okay? But now I tell you, no, Planck measure, Planck, the satellite measured the CMB, but we had to extract the galaxy because it was too bright, and we had to extract point sources, so there is a window function. You're not measuring in the perfect sphere. So now I will call the ALMs tilde the ones that contain the window function, okay? So I measure, what do I measure? I measure the solid angle subtended by each pixel. Now I have to sum over the pixels in which I'm measuring, okay? The variation in temperature is on the pixel. There is a window function that takes a value of 1 in the pixels that are measured and 0 outside, and the YLMs are measured, runs over the pixels, okay? So the pseudo-CLs, you saw the CLs, the power spectrum of the ALMs, but now the pseudo-CLs, they're called pseudo-CLs in the literature, are written as 1 over 2L plus 1, 2L plus 1, the sum over m from minus L to L, okay? And then I have A tilde LM squared, okay? This is the pseudo-CL, it's the same equation as the CL, but now I have the ALM measure in the window function. And the pseudo-CLs are related to the CLs in a little bit of a more convolved way. I miscalculated by one slide, I think. How this? I add one page here, yeah, like this. Awesome. So when I take the average of the pseudo-CL, what I get is a sum over L, a sum over L prime of GLL prime, CL prime, okay? Where this GLL prime, I'll write it in general, is equal to 2L prime plus 1 over 4 pi over the sum over L double prime, 2L double prime plus 1, WL double prime, and then I have L prime, L double prime, 0, 0, 0 squared. This is the Wigner 3J symbol. Perhaps you saw it with Julien or other people. No? This is known as the Wigner 3J symbol. Okay, and they are standard functions. Yeah, and what is this WL? This WL is related to, so this is 1 over 2L plus 1, the sum over M from minus L to L, WLM squared, okay? And what is WLM? Sorry, last one. WLM is the integral over the solid angle of the window function, YLM conjugated, okay? The usual. Okay, so if you know your window function and you can invert G, then you can know the true power spectrum. What you measure is always the pseudo power spectrum. Yeah, you always will have a window function. You never measure the power spectrum. You always measure the pseudo power spectrum. But it's possible to know your window function because you know your experiment. You know exactly what you're measuring, okay? So if you can, what is this? This is not a minus. I don't know what it was, okay? But if you can invert this function G, then you can go from the measured pseudo power spectrum to the true power spectrum, okay? So the last thing I want to add here is that, yes?
That point that you have mentioned, you mentioned, there is a recent paper that tell us about the mask and map are correlated. You cannot invert to obtain true pseudo-series from true CLs from pseudo-CLs.
If what is correlated, give me one, if what and what is correlated? The map? The map and the mask, but the mask is on the map. Okay, let's discuss this. Give me 1 second. I want to write this and we will discuss this later.